Question 5. Question 5 is a standard question on vector applications. If you've been paying attention in class, it should be quite doable at the A-level standard. And here, the heavy weightage of 10 marks telling you that the marker is giving you a free Christmas gift. So, ladies and gentlemen, appreciate the marker's heart. Do not throw it away. Otherwise, the next year Christmas, the marker is going to give it to someone special. And of course, you don't want that to happen. You want all of you to receive the free gift and the free marks that the marker is trying to give you. So, if you cannot do this question and you cannot score the marks, right, please go back and revise your hardcore content. I would like to mention again that, ladies and gentlemen, this question is very doable. It is all hardcore content. Okay? So, if you don't know how to do, please revise your lecture notes. And how is it hardcore content? I'm now going to force it down your throat. Okay? Pay attention. So, question 5a, as you can see, if you were to read the question part A, is going to be asking you for the vector equation of a line given 2 points, right? So, if you were to read it here, they give you points A and point B, right? And then moreover, they give L2 in the form of a Cartesian equation over here. It's a Cartesian equation. So one content knowledge they're trying to test you is, how are you going to convert the Cartesian equation of line into the vector form, right? Why is that vector form? It then leads me to the next piece of content, right? When two non-parallel lines intersect at the point, then how should I even be finding the point of intersection in the first place? And let me tell you, ladies and gentlemen, this applies to the equation of line regardless the form of its equation. It means regardless whether is it in parametric form or is it even in Cartesian form or whatsoever it may be. Okay? So, ladies and gentlemen, you know that by virtue of the fact that at the point of intersection, the two equations of lines satisfy each other, hence you're going to solve them simultaneously, and thus the technique of constructing simultaneous equations. But in this case, because the lines are expressed in vector equation form and vectors are in 3D space, so there are three components, so you need to construct three simultaneous equations based on each of the respective vector components, right? And then you're going to compare them and solve for the unknowns. But because this question is constructed in quite a way that requires you to go and solve two equations first, right? So you go and solve two first, and then after that you only solve the last. Because this question here, there are three unknowns. Okay, so the exam tips, of course, please revise your hack on learning from vector applications, right? Please refer to my vectors masterclass, which I'm going to release another day if you need further clarification. Okay, and then of course for this question, the question here asks for coordinates. So the question here asks for coordinates. Please be very mindful of the difference between position vector and coordinates, because this is a very careless mistake and it's not worth losing that 1 mark. 1 mark in a math paper is worth a lot, especially due to the high distinction rate by Singaporean students. All right, so I've directed you to my answers. Okay, so this one, I'm going to label it based on the content knowledge that you need to know, okay? Because I said already, this question is based on hardcore content. Okay, so I'm going to call this one C1, okay? I'm going to call this one C1. Find the vector equation of line given 2 points. So for line 1, here, when I find the direction vector, all the way to here, this is content 1, okay? Sorry, let me write my C properly. Give me a moment. So this one is content 1. Okay. Then for line L2, it's going to ask me to convert the Cartesian equation to a vector form. So this is going to be the content 2. This line here is content number 2. Okay, content number 2. Then by virtue of the way that I typically solve simultaneous equations when two lines intersect at a point, So I'm going to say here at point P, because I'm here going to show very, very explicitly to the marker that this equation only holds true at one specific point of intersection, in this case, point P, and in no other point does these two equations equate to each other or satisfy each other, right? And here, right, I've because lambda and mu is a parameter, right? It's a parameter that can vary. So I've written down there is only one value of lambda and mu for which this can exist. Okay, so this is what the word for some means. Okay, so if you ask me what I'm doing here, this is my content number three. My content number three, because this is how I typically go and find the point of intersection by virtue of the fact that the two equations satisfy each other. Okay, so now what I'm going to do is I'm going to go and start to solve these simultaneous equations. But then before that, you might have asked me, right? You might ask me, okay, then how do you decide very, very wisely in the exams which components do you solve first? Okay, so if you were to take a look at this case, you will see here that if you have to compare the first and third simultaneous equation, that means the I and K components, right? You'll notice that there are only two unknowns need to know. But for the second component, which is the J component that lies over here, you'll notice that there are three unknowns need to solve, right? There are three unknowns need to solve when you try to go and solve this component over here. So this means that this component over here, you should be solving last. You should be solving last as only after you have found the values of lambda and mu for which this equation satisfies, right? Okay, so basically what I've written here, comparing I and K components, because I want to illustrate my workings clearly to the marker, right? I constructed two simultaneous equations. Then after that, I'm going to solve them simultaneously. I don't think I need to explain how to solve simultaneously. Okay, so this is what I'm going to get. Okay, so after I've gotten this, right, I'm going to substitute these two values into the J components, right? And then after I substituted, I will only be left with one unknown. And this one unknown I need to find here is K. So I go and construct equation based on K, which is over here, right? And after that, I'm going to solve for K. And then once I solve for K, if you have done your calculations, everything all correctly, then K should be equals to 2, as what the question requires you to show. The question then asks for the coordinates of P. So before you can find the coordinates of P, you must reference it to the origin. So you find the position vector first, right? For me, I prefer to substitute lambda is equals to -1 because -1 is an easier number to go and handle as compared to -4. So I substitute it in here, right? Then based on this equation, the 7 + 6 lambda, I substituted into this equation, right? And after that, I'm going to get out the position vector of OP, right? But since the question requires for coordinates, please take out your yellow highlighter and highlight the word coordinates, right? So because this is the important one mark. So once I get the coordinates, I just need to write out in coordinate form. Okay, so I'm done with part one. Let's move on to part two. So as you can see, I've very visibly forced 5 marks down your throat based on this simple content knowledge of two lines intersecting each other. Nothing difficult, okay? Part B. So, part B says, find the position vector of the point on L2 which is closest to A. Ladies and gentlemen, if you do not know, draw a diagram. Okay, so I've very, very nicely drawn out the diagram for you, right? And some of you might be asking me, okay, what do you mean by the point that lies on L2 which is closest to A? Now, when you see the word closest, right, it is good that some of you will surely start to think of perpendicular. But what you need to be careful of is where is the perpendicular distance, right? So number one, the question already state it lies on L2. So because it lies on L2, right, this perpendicular distance is this point, right, it should be somewhere around here, right? It should be somewhere around here. Okay. And then moreover, right, you want to say it is closest to A. Closest to A, right? That means the perpendicular distance from A to a point on L2 should be the shortest, right? So, as let me say again, the perpendicular distance from A to a point on L2 should be the shortest, right? So we have drawn the diagram very well, and you are able to recognize that in this question, right, the question is actually asking for the foot of perpendicular of A onto L2. Okay, so this is actually a foot of perpendicular question. So something that you can learn from here, right? If something you can learn from here is that when you're in doubt, you have to draw a diagram, and after drawing a diagram, right, you notice that the point that lies on the line that is closest to the point A is the foot of perpendicular. Okay, so this means that in other words, the question is going to ask you for the position vector. Because why position vector? Because here the question said position vector. Right, I never read wrongly, okay? So the question is asking for the position vector of the foot of perpendicular of A onto L2, right? The foot means at the extreme bottom, right? So this the bottom of this perpendicular should be lying on L2. And that is precisely what the question is asking for, right? So this point over here, right? This point. So now that is when once you get this statement, it goes all back to hardcore content again. 3 more marks down your throat today. Hardcore content. How do you find the foot of perpendicular of a point onto a line? And if you have to see your lecture notes, there are actually 2 ways you can do it. So I've very nicely drawn up the diagram over here because I make it look like a projection diagram because one of the ways to go and find the foot of perpendicular is actually the projection method, right? So in this case, because it involves a line, right? So you're going to ask yourself, right? You're going to visualize this triangle, and then what you're going to find is you have to find this, right? You have to find this distance over here, right? So this is if you have to visualize it, it is going to be how far did the vector PA travel in the direction that is parallel to the direction vector of L2. So it's PA, vector PA relative to the direction vector of L2, right? Because this is the direction vector of L2. And then you're finding a vector that is parallel, right? So it is going to be this over here, right? So it's going to be Pn. Why did I say n? Because n is the foot of perpendicular, right? So n is the foot of perpendicular of A onto L2. So this is going to be point n. Okay. Then once you have identified this point, so I've going to identify here that, okay, I change the yellow color. This is vector PA. Project this onto the direction vector of L2, right? So it's going to be PA dot M hat times of M hat. If you want me to see the trick on how what we call make sense of all these projection vectors, right? And like all these parallel to the line L2, Pn is parallel to the line L2. All these tricks, please go and see my vectors masterclass, which I will release in another video. Okay, but nevertheless, moving on, this is again hardcore content. So, okay, so you can see here, PA dot, this is your M hat, right? This is your M hat, and this is times of M hat, right? So, and by then, you notice that as I apply this formula, I haven't found what is PA yet. So what I'm going to do is I'm going to find PA here, right? I don't think I need to explain how I find PA. It's just a simple vector subtraction. Okay, then after that, I'm going to just substitute all these numbers into the formula, right? Then slowly but surely, I work it out. This is the dot product, right? This is the magnitude of vector 1, 2, 2, right? This is the magnitude of vector 1, 2, 2, right? And then this part here is the vector, right? So that means whatever that follows behind, or sorry, whatever that follows on the left is all the scalar multiples, right? I think that's something that you need to take off because I've emphasized this sufficiently number of times in the vectors masterclass, right? Okay, so this is going to end you up in the scalar multiple of 8 over 3, and then it's 8 over 3 times of the vector 1, 2, 2. So this is Pn. Right now, what the question wants for the position vector of On because full of perpendicular. So I just need to do a very simple vector addition. This is OP, which I found earlier. That is the reason why the question asked me to find the position vector of OP, sorry, the coordinates of P, because I can connect it to part B. So this is what I mean by seeking a connection. Sometimes part A, part B, part C in the question is like a storybook like that. They want you to go and seek connection from one chapter to the next chapter, right? So I just need to do a simple vector addition. This one, you should know where it comes from, my previous step. And then after that, I'm going to get this answer. Then some of you might ask me, is it like possible to go and factor out the 1/3? I will say that no harm doing so. But for me, I go and prefer to leave it this way because it makes it more direct, especially since the question asks for position vector, right? Okay, this is just method 1. I say again, this is just method 1. Remember your content, hardcore content. Method 2 is the scalar product method. So same thing, I like M before perpendicular of A into L2. Then after that, I'm going to say that, oh, okay. At one particular point that is N. For some value of this scalar multiple that exists, On is going to be this equation. So let me highlight this equation. I don't know what has been wrong with my stylus. Okay, so once I express it in this form, right, then I'm going to go and find the vector NA or AN also can, because later on, regardless whether it's NA or AN, is still going to satisfy this property over here, right? So I very quickly going to use a very simple vector subtraction to go and find the vector NA, right? If it's AN, it should be the opposite. So it should be mu minus 2. Then after that, 2 mu plus 4, 2 mu plus 3, because it's just a simple negative scalar multiple. But nevertheless, this one is still okay, right? And then after that, I'm going to say that now, what is NA? NA is the perpendicular vector to L2, right? So this means that the two vectors are perpendicular. And ladies and gentlemen, please take note of this, right? Please take note of this. A lot of you tend to go and substitute the equation of line L2 here. This is absolutely wrong. The equation of line L2, it comes from a vector addition. If you are going to ask me where is ON, right? You can actually just bring the origin here and then after that, and then claim that this vector here is ON. Apologies for the not straight line. So you can actually claim that this vector here is ON, which is obviously not the direction vector of the line L2, right? If you want to ask to really know what is ON, right, please go and refer to my vectors masterclass again where I was talking about the vector equation of lines, okay? ON is not the direction vector of L2. The direction vector of L2 is called ML2. Okay, so going back to here, right? Those who shouldn't be substituting things like 5, 10, 8 plus mu 1, 2, 2. Later on, the mistakes they don't get very jialat already. Okay, it is a little mistake. It is a little mistake. It is a gross mistake. So please don't make it in exams. Okay, be very sure of what you're finding when it comes to the vector equation of a line. And refer to my vectors masterclass if you need clarification on that. Okay, so I've very safely say that, okay, they are perpendicular, and remember the 99.9% guarantee, the dot product is 0, dot product is 0. I'm going to use a simple dot product. I'm going to use a simple dot product expansion, right? And then I'm going to generate an equation in lambda. I'm going to generate an equation in mu. I'm going to solve for this unknown, right? And then once I solve this unknown, I'm going to substitute back into the vector equation. into this position vector of ON, right? Position vector of ON for this particular value of mu that causes it to satisfy the vector equation of line L2. And then same thing, I noticed that here I've gotten the same answer as L1, sorry, not L1, method 1. Okay, so I'm good to go. So again, here are the learning points, right? This is something that I've very jolly well discovered from this question, right? So when the question says that the point that lies on L2 that closest to point A, right? This is going to be the foot of perpendicular of point A onto L2. Same thing if the question asks for a point that lies on a plane that is closest to point A. Then it's going to be the foot of perpendicular of point A onto the plane, right? Same idea. And how did I know all this? Is because initially I was in doubt. So what did I do? I drew a diagram, right? In vectors, you're going to hear me say this until you are so sick and freaking tired of me. Please go and draw the diagram, right? Because vectors is sometimes is requiring you to go and visualize three-dimensional lines and planes, right? Then I can, like I said in my vectors master class, right? Vector applications are 50% about projection. So when it comes to projection, you must always identify what is the right angle triangle before you can even deduce what the formulas for the vector projection are, right? And of course, this again, very solid foundation. The marker wants you to earn the 10 marks and have very successfully credited 8 marks to you down your throat, right? So please build the solid foundation, okay? I don't have to talk much. Then after that, 5C is of course a very standard reflection question, right? They say vector equation of a line which is a reflection of L1 in L2. Okay, ladies and gentlemen, read the statement properly. Reflect what in what? Reflect A about B means B is the mirror. I say again, reflect A about B means B is the mirror. And A should be on the opposite side of the mirror, right? So it's the same, it's like saying, oh, reflect L1 about L2, right? Reflect L1 about L2. So same, so as what this question says, right? I'm going to reflect L1, right? Let me use a pen. I'm going to reflect L1 about L2, right? Reflect this whole thing about L2. So I'm going to shift it to this opposite side over here, right? So because I shared it to this opposite side over here, right? That's why I've generated L1 prime, which is a mirror image of L1 about L2. Okay? So as you can see here, because this point lies on L1, right? So there's also going to be a mirror image here. I call this point A prime, right? And then obviously you can see I've drawn out this triangle over here very, very nicely for you, right? So ladies and gentlemen, when you do reflection questions, because of the mirror image that exists, there is one very special property of the ratio theorem that you can use, which is the distance of AN is the distance of AN prime, right? And that's the reason why you need to go and find the foot of perpendicular in the first place, right? And because here the question is asking for the vector equation of L1 prime, you need the direction vector of L1 prime, right? So you have no choice but to go and find what is this vector over here, PA prime, right? You have to go and find this vector over here. So how do I find this? Go up finding this vector, of course, now other than using a ratio theorem, right? Straightforward, hardcore content, right? Then after that, make sure you have no careless mistakes. I'm supposed to go and get this out, right? And then because you see here, I can easily find out the 1/3, so I don't necessarily have to deal with very ugly numbers, right? And then here I've deduced that this is the direction vector of L1 prime. Why? Because PA prime is parallel to L1 prime also, and I factor out the scalar multiple, so nothing much of an issue, right? Then some of you might ask me, do I need to know what is this point here, A prime? Answer is no. Because vector equation, what do I need? I only need one fixed point. What is the, and if you can see carefully, this is already a fixed point that lies on L1 prime. In fact, it is the point of intersection that is the point of intersection between all three lines, right? simply because of this special property of the mirror image and the information given in part A, right? So this is of course the position vector of point OP, right? The position vector of a fixed point on the line. And this, I'm going to use a different scalar multiplier. This is alpha, right? And this one is none other than the direction vector. And please remember to go and write this statement. If you don't write this alpha is real, right? Then it is incomplete to the vector equation of the line, because a line is made up of infinite number of points. So there are infinite values of alpha for which the vector equation exists, right? Okay, so this marks the end of my review to question 5. Thank you for your attention. Goodbye.